Okay, so hopefully you were able to fill in all those blanks on pages 3 through 5 for some practice. Let's go over some possible answers together. So the lab manual gave you a scenario where you're studying tomato plant growth. Okay, what are some possible dependent variables that could be measured in an experiment like this? And remember, dependent is something that the researcher measures in an experiment. So in this case, what could we measure to help us learn about tomato plant growth? Okay, so some examples of dependent variables could be height of the plant, could be weight of the plant, could be the number of tomatoes, the number of leaves, anything that's helping you to measure the growth of the plant. What about independent variables? So independent, if you remember, is something that is directly manipulated by the researcher, something the researcher is controlling in the experiment. So in this case, what are some factors that could affect the number of tomatoes produced by the tomato plants? Okay, so some examples might be sunlight. Maybe you have different sunlight exposures for different groups of plants. Maybe water level, maybe fertilizer. Okay, these are things that you could control to see how it affects the plant growth. All right, how about controlled variables? This is something that's held constant in your experiment. So in this case, the lab manual said that you are studying the amount of fertilizer and how that affects plant growth. So what would be other factors in this experiment that need to be controlled and kept constant? Okay, so this would be things like the type of fertilizer, or sunlight levels, or water levels, or soil composition, or tomato plant type, right? These will have to be the same between your different control and treatment groups. Okay, let's do another practice example for identifying independent versus dependent variables in an experiment. So I'll read through this. Hunt and her team administered daily doses of BPA, and BPA is an industrial chemical that's sometimes found in plastics, FYI. They administered daily doses of BPA to groups of female mice over 3, 5, or 7 days, and then tested these mice for genetic abnormalities. Okay, so you can kind of see that laid out here in the picture. Each column is a different group, so 4 different groups, with different dosages of BPA. So this group has no 0 BPA. This is 20, 40, and 100. And then it's showing just the fact that this BPA is administered over several days. So on day 3, day 5, and day 7. Okay, so identify the variables as independent or dependent. These 3 variables here. Pause the video and think through this. Try and actually identify each of these variables. Okay, this is the answer. So dosage of BPA, this is independent, something that the researcher is manipulating. Time of exposure, how many days are they given BPA? This is also something that's independent. Percent of abnormal mice, this is dependent. This is what you're measuring in the experiment. Also, what might be a positive control and a negative control for this experiment? Okay, so this is tricky. Pause the video and try and think about this. All right, a positive control. Something already known to produce the expected phenomenon. So in this case, a positive control might be another group of mice where you give them some other drug, drug X, whatever, some kind of drug, that you already know causes genetic abnormalities. Okay, and why might you want this? It's just an extra control to show that, hey, these mice are able to get genetic abnormalities, right? This is something that can happen in these mice. What might be a negative control for this? This actually would be the first group right here that is not given any BPA. Okay, in the real experiment, if this were actually done, this group right here would have to receive injections, just like the other groups, but there's no BPA inside, right? You want to control for everything, make everything the same, except that they get no BPA. All right, there are a few other things that you need to consider in designing an experiment. One is testability of that experiment. So you have to be able to test it out in order to design a good experiment. It's something you have to actually be able to test. Okay, so you can come up with all sorts of hypotheses or explanations to some natural phenomenon, but if you have no way to test it out, the scientific method can't help you with that. Also, repeatability. So you must be able to design an experiment that can be repeated. Repeated and then where someone else could get similar or the same results as you. A lot of high profile research is actually not repeatable. This is a big issue now in the research world, is that you get these scientific papers published in big journals and then other groups try to replicate the data and they're not able to do that. So this is something that researchers are thinking a lot more about in recent years, is we have to make sure that the experiment that we're designing can be repeated and that similar results will be obtained from that. Also, sample size. This is how many participants are in your experiment. Okay, so for example, for the tomato plant example in your lab manual where we're looking at plant growth, this would be the sample size would be the number of tomato plants that you use in your experiment. For the mice example, BPA example, it would be the number of mice would be the sample size. Okay, it's just the number of participants in your experiment. And this is really important because with a small sample size, you can't really draw any conclusions. So what you see might have just happened by random chance, but you don't know that for sure because your sample size is really small. So ideally, you want as many participants as possible. The bigger the sample size, the better. One relevant example that we've seen showing the importance of sample size has been in the news recently, and it's the use of hydroxychloroquine in treating COVID-19. So in March of this year, 2020, a study came out that seemed to show hydroxychloroquine could be used as a treatment in COVID-19 patients. So this is a drug that's usually used to treat malaria, but in this study, it seemed to reduce the viral load in COVID-19, meaning that patients had less virus in their body if they took this drug. Okay, so this study came out and this exploded all over the media. It seemed like everyone was talking about hydroxychloroquine. Okay, even President Trump was talking about it a lot and promoting it. It was huge. Okay, but this study actually only treated 20 people with the drug. And their control group was only 16 people. Okay, so this is actually a tiny sample size, and it's hard to draw any real significant conclusions from this. Okay, and then in May 2020, 2 months later, another study came out, and this was a massive study. They had a sample size of 96,000 people, okay, and 15,000 of those were treated with hydroxychloroquine. So this study found that the drug actually lowered survival rates rather than help treat COVID-19. Okay, and that's terrifying, right? Something that we initially thought might help treat the disease actually made it worse. Okay, so this really shows the importance of a large sample size. Okay, so those were a few of the basic considerations to have when designing an experiment. And as you're learning about this, I want you to keep in mind too that knowledge is power. These things might help you design your own experiments, sure, but many of you aren't planning on becoming scientists. But this is still useful for you. These things are going to help you to recognize good research. So flawed science unfortunately happens a lot more than we know, a lot more than we want it to. Flawed science can and has impacted healthcare treatments and policies. But if you become familiar with these elements of a good experiment, you can also learn to distinguish between good and rigorous research and then poorly designed experiments where you shouldn't be drawing any conclusions.